Yeah, so good evening everyone. I think we are good to start. So this is our second class. So we have been discussing on, so this is the topic that you know. So last day we started with the understanding of field. So by field what do we mean? The conclusion is spatial distribution. And when we talk about magnetic field, then what do I mean? What we mean is spatial distribution of magnetic field. And we understood that magnetic field is due to some current carrying conductor, and we visualized some simple cases of distribution of magnetic field due to current carrying conductors. So this was the first case, only one current carrying conductor. We understood that all the flux lines are basically enclosing the source, and they are all flux lines are closed, they are not open. So all, unlike electric field, magnetic flux lines, unlike electric flux lines, this magnetic flux lines are always closed. And so we understood the different properties, and we understood that field lines can be are a good representation of the magnetic field, where the density of flux lines, they indicate the magnitude of the field, and at any point the direction, basically the tangent indicates the direction of the magnetic field. We saw the case of two current carrying conductors also carrying current in the same direction. Then we saw the case for two current carrying conductors of opposite polarity side by side, and what happens, the field due to that. And then we saw three such cases side by side placed, and we saw understood the field because of that. And we saw that as we have more and more number of turns, then we tend to increase the strength of the magnetic field at the axis. We also understood about the axis of a magnetic field. Uh, it's the imaginary line at the middle that is not crossed by any of the flux lines. That is the simple definition of magnetic field. Then we saw till now whatever we discussed was the case for current carrying conductors only in here. Now we introduced some iron also, and here we saw that flux density in the iron is significantly increased, significantly more compared to flux density in here. And regarding this there was a question in the group also. So the question, so first part of the question is, are all the flux lines actually enclosing the field? Are actual all the flux lines, so basically flux lines always form closed paths, but when we have air gap, it seems that the iron has more flux lines where the air has less flux lines. So it is, all the flux lines are closed, and here the picture that I have provided is actually a cropped version of that. So actually all the number of flux lines are actually the all the flux lines are equal, and all the flux lines are having some path through air, and some portion of the path through air, some portion of the path through air gap, or basically air, as it is not a small air gap only. So I will just uh, show several flux lines for you. So this is one flux line which is a closed curve like this. You can see another flux lines which is also a closed curve like this, and they never intersect. So if I go to the other, so this seems an disconnected line, but actually if I show you the complete picture, it would look like something like this, and same goes for these flux lines also. So all these flux lines are actually closed paths. It is not like any of the flux lines are having are discontinuous. And similarly on the right hand side, you can see this is the closed path of a flux line. Again this is another flux line which is again closed, and similarly for these lines also it is something like that. Now what you can see is, uh, so if I go next into the question, total flux lines entering the air gap, the total flux lines coming out of the iron is equal to total flux lines entering the air gap. That is true, but because in air gap, or basically in air, the flux lines tend to get distributed, so the flux density, so the, as correctly pointed out, the flux lines per unit area, that basically reduces in the air. All the, but because iron is highly permeable, so all the flux lines are very densely packed within the iron. That is what makes us or gives us this uh, picture that iron has very high flux density. So I hope it clarifies the question. So first point, all the flux lines are closed, and because in air they tend to get distributed, that is why you have less flux density in air compared to iron. And because of very high permeability, all the flux lines are basically packed within the iron core. So after that we saw the case for iron core with a very small air gap, and we have some turns around it, so we can create very high flux density in air, and that is important because air has anyway, so flux density is high, and flux density by mu 0, that is also quite high compared to iron. So if you see here, whatever is the flux density, almost same flux density is here also, but here when calculating H, it has to be divided by the mu r of the material, which is tens of thousands, but here it is mu r equal to 1. So you have very significant high H, high magnetic field intensity in this zone, which causes, which enables us to store a lot of energy in the air gap, which is of beneficial or of benefit to us. So that is why most of the magnetic circuits, like say air inductors or electric machines, we generally keep as very small air gap. Then after that, what we discussed is we
Samrat, before you go to the next slide, can you go
yes,
to previous one? So in the first two figures, can we actually define what is the area in the air gap? Because it's like the entire field outside iron bar, right? So
yes.
is there any definition for area in the air gap or?
No, 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 it does not have. So we have to, it can only be answered by dividing the total air portion into small, small areas, and we can have B distribution. There is not a area of the air gap. So similar
Yeah,
to this, so area in this case you can see
which
that
case?
we have a small air gap,
Yeah,
so somehow we can either define this to be the area that is equal to the iron core, or we can introduce some factor that takes care of fringing, and we can define some increased area of the air gap. But those all are approximations that we are doing for our simplicity of calculation. When air gap is bigger, then we have no way of defining any air or area of the effective area of the air gap.
yeah. Thank you.
Okay. So we discussed on that, uh, how do we realize the stator of a DC machine. That is basically an iron core coil, and um, that is the stator. We have some winding in the so we have one dot conductor, cross conductor, again dot conductor, cross conductor, and this is the field that you can have. So because here flux lines are going upwards, so this surface the flux lines are entering, that is why it is south pole, and from this stator surface the flux lines are coming out, that is why it is the north pole. So we discussed these in details. Then we looked at the principle for torque production to magnetic fields. We saw some simplified examples, but our conclusion was for continuous torque production we need two magnetic fields. So we need two magnetic fields, and they have to be stationary with respect to each other. uh, but with certain angular shift. They needs to have some angular shift theta. So pictorially representing, if this is one magnetic field, if this is another magnetic field, there has to be some angular displacement between the two, that is theta, and this theta should remain constant with time. So we discussed that we can realize this with three or there are basically two cases, two possibilities that we can have. If say this is rotating this field with respect to a stationary observer that is rotating at some angular velocity omega 2, and this is rotating at some angular velocity omega 1. So first case is we can have both omega 1 is equal to omega 2 equal to 0 in that, and there is some phase shift, there is some angular displacement between the two. So in that case we can have continuous torque, and that is the first case. And the next case is where omega 1 is equal to omega 2, where both the fields are rotating but they are rotating at the same velocity. So if at time equal to 0 there is some angular shift between the two, because both are rotating at the same speed. So even time equal to t1, here say f1 comes, then f2 will be here, right? So the same angular displacement will be maintained. So this is the second necessity, or the second possibility of having continuous torque production from this basic idea. Now we will see briefly how do you realize the stator magnetic field, that is F1. So for F1 the speeds are basically omega 1, and F2 the speeds are basically omega 2. F1 is field due to stator, and F2 is basically field due to rotor. Of course rotor winding or some excitation, stator winding, I would say. So first we have to see these things, that how to produce F1. So how to produce F1, that is what we will see, how to produce the magnetic field due to by stator. So first we will see the simple case, how to create stator magnetic field that is not rotating, that is omega 1 equal to 0. So that is the first case, realization of stator magnetic field, how to create stationary stator magnetic field. That is simplest case. You have uh, I have just created the same picture that we have developed, that is the stator of an DC machine, of a DC machine. So we have two poles and we have two sets of winding on the poles. So this is how the winding, the current is basically passed through it. If this is dot, this is cross, and this is dot, this is cross, so that both of them aid each other. Now if we look at the field in space, so let us see what kind of B distribution is there in the air gap. So for this I have indicated this red circle at the air gap. So this point I will probably use some other color. So this point is theta equal to 0, this point is theta equal to 90 degree, this point is theta equal to 180 degree, this point is theta equal to 270 degree, and again we come back, as we keep on moving on this air gap circle, we again come back on this point where it is theta equal to 360 degree, which is nothing but theta equal to 0 degree. So if we excite the winding like this with certain DC current, so just to give you some idea, so how is this winding placed. So if so this is how it is wound around this pole, right? This is how it is wound and it is coming out. And again for the next one also, you have the same way, same sense, the windings are basically wound, and they are basically put in series. So if I is passing through this, I is coming out from this, and the same I is basically injected into this, and the same I comes out of this. So these are the two terminals of the winding that we are having now. And now we will see what is the field, what is the B flux density in the air gap on different points of this air gap circle. So let us go to that. I'll remove this portion for better visibility. So this is how the B or flux density is distributed in the air gap. As you can see, under the pole, that is, this is 90 degree, and on two parts of this pole you have some non-zero flux density, right? This is some non-zero flux density, and this also gives you the answer why we increase the pole shoe area. Had we not increased, our distribution would only look like something like this, right? This is how our distribution would look like, but we want to have more non-zero magnetic field in the air gap. That is why we tend to increase the pole shoe area in order to have more area with non-zero flux density. So because it is basically going up, and we define that any flux density that is radially going outward, we define that to be positive. That is why under the south pole it is having plus flux or positive flux density, but on the other side, on the diametrically opposite side, that is under the north pole, flux lines are basically going upward, that is radially going inward, right? I think you can see this. This is the center, this is the radius, so the flux lines are going radially inward. That is why it is the same flux density, but it's the negative. It is the negative flux density under the opposite pole. Now if the because the current is stationary, or current is DC, so the current excitation does not change, so even the field distribution in the air gap, that also does not change. So that is how to realize a stationary magnetic field. That is the simplest case, right? This is the simplest case of producing a stationary magnetic field. uh, so this is what we find in a DC machine. And next
Samrat, one
next
question.
yes,
So we are finding this B in air gap, right? So at each
yes.
point in that red circle, are we seeing how much B is coming out tangentially? Is that what the plot says?
No, it's the
Or
plot,
radially?
how much B is radially going out
Radially, sorry. How much B is coming out radially at each point on the circle?
on each point on the circle. That is correct.
Yeah. Okay, thank you.
Yeah. So this is the stationary magnetic field that you have realized already. Next we are going to realize how do we get a rotating the magnetic field to rotate, right? So we'll start from this.
Samratji,
Yes,
one doubt. So
yes,
here we are giving a constant DC voltage and DC current. How
yes.
this back EMF is created?
Do not
Is
come
this
into back
rotating?
EMF right now. When we as of now,
This
just
is what is this? What is this? This is rotating. This rotor is rotating.
no, nothing is
Just
rotating.
one rotation.
No rotation
Just
at all.
we are giving a supply. That's it.
Just we are giving supply there. You can see nothing is there in the rotor. It's only a cylindrical body, cylindrical ferromagnetic
Oh,
material. No conductors
oh,
are there, nothing is there. So we are only
okay,
exciting
okay.
the coil, and we are looking at the
Uh,
field. So this is how the
okay,
stationary magnetic field look like.
okay,
Okay, we'll see why back EMF comes and other things.
Uh,
Yeah.
okay.
Sir, one
Got it,
doubt.
got it.
excuse me. Yeah, one thing,
Excuse
sir.
me, sir.
So you were saying
Yes,
like at 90 degrees, it was like a angular position. Whenever the 90 degrees, there will be
yes,
the more flux density. Yeah? You
yes.
mean 90 to 70.
Yeah. So 90,
Okay.
this is 90. So under this pole you will have almost uniform flux density everywhere. From this point onwards, which is this
Mm.
point, and up to this point, which is basically this point, up to this you have almost uniform flux density that you can see.
So, okay. Okay.
Samrat, one more
Sir,
question.
one.
If we had two
Yeah.
more poles on the 0 degree side and 90 degree side, so would we
Yes.
have had a complete square that time?
Two more coils. How?
Uh,
Poles.
two more stator poles and at the zero
Yeah,
degree
coils.
side and 180 degree side, and then we excited
So
them also.
you want some separation between the poles also? something like this. So you have one pole, you have another pole,
Yeah,
you have
correct.
third pole, you have
And the
fourth
fourth
pole,
pole.
and you excite them,
Yeah.
right? So that this is
We
north
give
pole,
the
this is
same
south
DC
pole,
excitation.
this is north pole, this is south pole,
Correct.
right?
Yeah.
Then if we have the same kind of rotor,
Hmm.
then basically we would not have perfect uh, or square, not perfect square wave, but it would look like
Okay.
this. It is under under south pole here, so it will be positive here, then negative here, positive here, negative here. In between it will fall like this.
Yeah. So it will
or
be
it
more.
or it could also have some zero
Oh,
flux density region like this.
okay.
It depends on how we design. If our design is like this, then
Okay.
you can see that in between there is almost no iron available for the flux lines to go. So you
Yes.
would have almost zero flux density here in this region. Under the pole you will have positive. But if we increase the pole shoe
Correct.
in this way, in this sense that there is almost
They're almost
no
touching
year
each other.
gap,
And
yes,
yeah.
then this zero stay would be negligible.
Okay.
Sir,
Thank you.
that I have a doubt.
Yes,
When we have a four pole
yes,
and that flux density is like developing like a quasi square, like a zero level with high.
yeah,
So it will be a like in 360-degree, that will be a four, like a complete
four poles,
two
yes.
cycle we are seeing, or it will be of like 360 plus 360. Like, what is the angle value that that I want
We
to ask?
will see, we will understand what we mean by electrical angles and mechanical angles. So mechanical angle, as you can, mechanical angle remains fixed, right? Mechanical angle is nothing dependent on the excitation, but we will see
Yeah.
what we mean by electrical angle and mechanical angle.
Okay, sir. Thank you.
Sir, one
Okay,
doubt.
yes,
Sir, actually, yeah, actually, sir, this waveform is a quasi square wave.
yeah.
Can we make it as a square wave, or is there any restriction because of the leakage which is happening?
As of now, let us not try to get into that. Let us try to understand what do we mean by stationary magnetic field, and can we make it rotating? Okay.
Okay, sir.
So as of now, we'll skip this. Can we make it square or other things? Yeah. Let us try understanding how. So first one we have realized. First one we have realized that, okay, so stationary magnetic field we have already realized. Now we are going to go into the realization of the rotating magnetic field, starting from basics, starting from the same structure only, right? So you would have, we have the same thing, we have the same thing, only for simplicity I have removed the pole shoe. We do not need it now for understanding. So this is the same structure that we are having, and we are having the same type of winding, and we are only, the only change that we are having is the current. Instead of a constant DC, in this case this is not DC, this is an AC current, a sinusoidal current that we are injecting into the coil. You know that both the coils are connected in series, so we can simply, so here is one terminal, the other terminal goes like this, and this is the terminal. So this is the current that we are injecting, and this current basically looks like this with in time. So now you have to be careful. This is 0 to 360 degree. This is omega t. Omega t is basically time angle. So this is angle which is dependent on time. With time this angle keeps on changing. So that is what we mean by time angle, and basically current is basically sinusoidal with that excitation, which the excitation that we are giving here. So let us try to see the animation of field, how it looks if we give that type of excitation. right? So if I run it again, then you can see that initially when you have zero current, then there is no field in the air gap. As current increases, then your field starts getting developed, and your field starts becoming stronger and stronger. And but the axis, one clear thing that you can notice in this case is the axis of the magnetic field always remain same. So although the current is changing and the field strength is you can see the pulsation in the field, so the flux density values are changing with time, but that does not cause the axis to change. So still it is a stationary magnetic field only, but the magnitude of the magnetic field is varying with time, because we are changing the magnitude of current sinusoidally. That is why the flux density is also changing. Now we will try to see what happens in the flux density distribution along the angular position. So this is the same red circle that we saw earlier. So if we draw a red circle at the air gap, right, this is our theta equal to 0 degree. This theta is spatial angle, this theta has nothing to do with time. So this angle is spatial angle, and this is 0 degree at this point, 90 degree here. So we are traversing on this red air gap circle, and we are saying what is the flux density on different points of this red circle. That is what is plotted in the right hand side picture. That is the radial component of flux density versus the angular position. So this is the x along the x axis, 90 degrees along the y axis, then 180 degrees negative x axis, then 270 degrees minus y axis. This is again coming back to 0 degree, that is the positive x axis. And the left hand side picture, this blue dot will indicate at what time instant we are at. So currently we are at omega t equal to 0, and also omega t equal to 0 degree, right? And as I run this animation, you will see that this blue dot will shift from one place to another, and the corresponding changes will appear on this right hand side picture. So we will be progressing in time, and accordingly we will see what is happening in this biradial versus angular position plot. Right, I think you have seen that. So I'll just stop it at multiple instance for you. So initially we are at the 0 degree, that is omega t equal to 0 degree, because the current is 0, so there is no flux density in the air gap. Now if we as we jump to the next point, that is almost omega t equal to 30 degree as far as I remember. So yeah, it is 30 degree only. So there is some positive flux density, positive current. So because of that, there is some positive flux density under the at 90 degree, or on the two sides of 90 degree, and there is some negative flux density on the two sides of 270 degree. Now as we go to the next point, that is omega t equal to 60 degree, then you can see that flux density value increases because current value also increases. Then as we go to the next point, omega t equal to 90 degree, it further increases, and it reaches the maximum flux density. Then as we go down at omega t equal to 120 degree, it comes down. Then further 150 degree, it again comes down. 180 degree, because current again goes to 0, it becomes 0. Then because current reverses its direction, so the flux density wherever you have, so under at the y axis, that is omega theta equal to 90 degree, you had positive flux density earlier, and you had negative flux density at theta equal to 270 degree. But now because current has changed, so you have the opposite case, that is you have negative flux density at 90 degree and positive flux density around 270 degree. Now As you go forward in time to 240 degree, it further increases, then it reaches negative maximum, then again it comes down and reaches the same point where we started from. So this is what is happening in the in the spatial distribution of B along that air gap circle as we excite the coil with one sinusoidal current. Now we saw what happened due to a single phase excitation. Now we'll try to say we have three phase. What is the what can we do? We can have three phase shifted sinusoidal currents, that is what you know. But how to connect the coil, how to place the different coils, and so earlier case we saw that we had only one phase, so we had placed the axis of our magnetic field axis. You can now understand that this axis indicates the direction of magnetic field if positive current is excited. If negative current is excited, then this will flip, right? So if we have three winding or basically three phases, then what type of structure first what type of structure naturally would come to us? So let us try to so if we have three phases, that means three magnetic axes, what can we do? We can for the most symmetric case, let us try to align or let us try to have them phase shifted from each other symmetrically. So if so they will be symmetrically, that is 120 degree phase shifted with respect to each other. So this will be the next phase, and again this will be the third phase axis. Now how do we realize that? How do we realize that magnetically? We had one pole, right? We had one pole, and in order to produce the magnetic field axis like that, we had put dot conductor here, cross conductor here. Similarly, dot conductor here, cross conductor here. That is the case we had taken. Now for the second phase, or basically the second phase axis, we would create a similar thing. We would create a similar uh, structure, and in order to have the direction like this, what do we need to have? We need to have cross here, dot here, again cross here, dot here, right? Applying the right hand side rule, this is the axis, this is the axis of the green phase axis. Now for the third one, that is the blue one, right? This is the pole that we have created, and in order to have this as the axis direction, what do we need to have? We need to have dot here, cross here, again dot here, cross here. And once we have this 6 pole structure, we can close them, we can close the path, and we can put some yoke to for the flux lines to complete their path, right? Similar to the earlier case only. So this is the case that we are going to look at as of now, that is the three phase one. Multi-phase, say if we had 4 phase or 5 phase or 6 phase, nothing, it's the same thing, same business that I had done. You have to put that you can realize the same thing by just having the appropriate appropriate angle difference between the two, because we had 3 phases. So the phase shift between the 3 axes was 360 degree divided by 3, that is 120 degree. Obviously we are talking about mechanical, so it is angle in space, that is the angle a child knows. So as of now I'll just tell it 120 degree. When something else comes, I'll come back to that. If we have some m phases, then the phase shift between the different axes have to be 360 degree divided by m, and you can create a similar structure and do and see what happens. So obviously for m phase, the angular shift between currents, they also have to be one appropriately, so 360 degree divided by m. In 3 phases, we have the 3 phase axis phase shifted by 120 degree from each other, and we have the 3 phase shifted currents injected into them. In case of m phase, we would have the m phase magnetic axis basically phase shifted them from by 360 degree divided by m, and the currents will also be phase shifted from each other by the same angle. So let us see the structure that we have realized. So this is the R phase axis, you can see dot cross, this will create the R phase axis. Similarly, we have the yellow phase axis and we have the blue phase axis, and we will inject. So we have three phase windings, we will inject three phase sinusoidal currents to that, and you can see that these are the three phase sinusoidal currents which are balanced. So at any point IR plus IY plus IB is equal to 0. That we are taking just for simplicity, and that is the three phase balanced case that we know. And you can see that the red phase zero crossing is here when it is going from negative to positive. Yellow phase or green phase zero crossing is here when it is going from negative to positive, which is basically 120 degree, lagging the R phase by 120 degree. And similarly, the blue phase zero crossing is again lagging from the green phase zero crossing by 120 degree. Similarly, again red phase zero crossing is basically lagging from the blue phase zero crossing by 120 degree. So this is the kind of excitation that we are giving, and next we will see what first let us see what happens if we give this type of excitation, what happens to the magnetic field. Now I'll start the animation, so you can first try to see that. Right, you have seen. So now I'll try to show you by stopping at multiple points. So for initially the axis is something like this. You can see I have drawn the axis at this point. Now as I go ahead in time, then you can see that the axis has actually shifted and the axis has come here. So there is some kind of rotation in the axis. Now as I go ahead, you can see that now this is T1, this is T2. Now the axis T3 axis has come here, right? As we go forward, you have the T4 axis. So you can see that we don't know how, but we have a rotating magnetic field. So if we have three phase axis phase shifted from each other by 120 degree, and if we excite them with three phase shifted sinusoidal currents, then we see from the results that we have a rotating magnetic field. Now let us try to see that at multiple instances as we saw it earlier. So this is the same thing. In this case we have a black circle at the air gap, and this is the 0 degree position, this is the 0 degree position, this is 30 degree, 90 degree, 150 degree. So the omega t equal to 0 degree, that is this line, omega t equal to 0 degree. This is how the flux density distribution look like. So because we have basically zero phase A current, so there is no flux that is going here through this A phase. So the net flux density look like this. I will not go further details here into the explanation of this. And next, if I go to the next instant, that is omega t equal to 60 degree, then you can see that the distribution, flux density distribution basically changes. And now we will see the animation, what happens as we go forward in time. Yes, so you can see that there is some kind of traveling wave that is there in this case in space as we go forward in time. So as we at this instant, if I try to so this is a periodic signal. We can take Fourier series and plot the fundamental sinusoid from this, and you can see this is the fundamental sinusoid. Now as we go ahead in time, I will go by two steps. because that would show the waveform to be the same, to be symmetric. Now you can see that we have two type of instance, because I am going only by 30 degrees. One type of instant where one of the currents is basically 0 and other two currents are equal but opposite. For that we have B distribution like this. Another condition, if we go ahead by 30 degree, then we have one phase having a peak current, another two phases are conducting equal currents but half the peak current. So in that case we have non-zero flux density under each pole, and we have this type of distribution. So if I go ahead, then you can see that the sinusoid, the same sinusoid that I was trying to draw, if I try to draw it now, the sinusoid has has shifted. And if I go further ahead, right, like this case, you can see that sinusoid has further moved. So as you can see visually here also, that in the B distribution, as you go forward in time, the B distribution, basically there is a traveling wave in that, and there is continuous rotation. So because it's a wave, so it keeps on getting changed. So this is the B distribution that you can have. And another thing, just to look at things once more, I would remove those so that you can clearly see. So now we will see. So this was the peak of the sinusoid when we started, right? This is the peak of the sinusoid, or the fundamental sinusoid that we are trying to see. Now as we are going forward, this is moving. Now we have completed, now we have completed half the, basically we have moved ahead by 180 degree in time. So the sinusoid has also moved. So the B distribution, the fundamental of that has also moved, the peak has also moved by 180 degree. You can see that this is 180 degree. So when we are moving ahead in time by 180 degree, we are also seeing that the B wave is also moving ahead by 180 degree. And as we go on further, as we complete one cycle, that is electrically we go 360 degree, we can see that the same thing, the sinusoid has also traversed its complete thing, and it has come back to its original position. So we can see that for this case, at least, if we traverse one electrical cycle, the B distribution is also traversing one cycle in space. So there is no confusion. Whatever is our electrical degree angle, that is omega t, that is same whatever at whatever velocity the B is rotating, that is the same. So what do we so you have, because you have taken electrical in the basic course, right? So what do we actually mean by the term synchronous speed? So you know the formula for that, right? 120 F by P, that is the rotations per minute. What is this actually? It is nothing but, so for F equal to 50 hertz, so if we have F equal to 50 hertz, and if we have two number of poles as we have in this case, so what do we mean by two poles? You can see at any instant of time there is only one, so there is in net there is one north pole and another south pole, that remains constant. Although it is rotating, although the magnetic field is rotating in space, but at all the instants we have one north pole and we have one south pole. That makes it the case for a two pole machine. So if we put p equal to 2, and if you just plug in values to this expression, you will find it to be 3000 rpm. Is it correct? Yes, 16 to 50 equal to 3000. Now what is the meaning of that? That is nothing, that is simple actually, where there is no so f is equal to 50 hertz. What does hertz mean? Hertz means there are 50 cycles per second. And what does rpm means? How many rotations or how many revolutions per minute? So what do we need to do? We need to simply multiply this 50 into how many seconds are there in a minute in order to get the value, right? So this is the corresponding the synchronous speed is nothing but the corresponding uh, the speed corresponding to the excitation frequency. If we are exciting with 50 hertz, then we will see 3000 rpm. If we excite by 25 hertz, we will see 1500 rpm. So synchronous speed is nothing but the speed corresponding to the excitation frequency that we are exciting our coil with. Yeah, so it's clear. So we understood that how to produce a rotating magnetic field. Now we'll see
One
is this.
question.
Yes.
So in this case, the excitation had three sinusoids which are distributed at one or
Yes.
time shifted by 120 degrees, right?
Yes.
Suppose if it was not 120 degree shifted, suppose all of
Yes.
them were having same phase or some phase which doesn't make them balanced, or
Yeah.
then we will not have this, or we will have some other motion.
Then we would not have this rotating magnetic field.
Okay.
We may have some pulsation may be there, but there we will not be able to see a magnetic field that is rotating at constant velocity of omega.
Okay. So
You
if
may see that.
everything is same sine wave, if everything is
Yes.
sine omega t, then it will not rotate. It will be the same case as you showed in case 2, right?
Yes.
Where there is
if all of them are
continue.
If you mean if all the currents are the same, right?
Yes. Yes.
If all the currents are same, then
The
at
windings
any
are spatially
instant,
distributed, but
yeah,
the excitation is not time shifted.
time shifted, then you can just look at what will happen. So say some current is there, then what will it produce? It will produce a south pole. It will also produce a north pole. It will produce a south pole. It will produce a north pole. It will produce a south pole. It will produce a north pole. So you will have a thing like this, which will be continuously changing its signs. So north will become south, south will become north. So you will have this type of structure, this type of distribution of magnetic field.
Okay.
You will tend to have, say, how many poles? You tend to have 6 poles.
Okay.
Not 2 poles. And it will not rotate. It will just keep on pulsating.
Rotate. Yeah, it will be this case 2 where you had only 2 poles and a sine wave, I think.
Yes,
It
yes.
might have.
It
Okay.
will be the same thing like this.
Yeah. And any other phase will not have this rotating motion, but it might have some other motion, is what you're saying, right?
Yes.
Thank
It
you.
will not have this rotation, continuous rotation.
Okay. Thank you.
Yeah.
Sir, it will not rotate. No, sir.
Samrat, one more
It
question
will
here.
only
Yes.
pulsate only.
Yeah, something we are seeing like above 3 phases, right? 6 phase machine, something like that.
Yes.
How it can be realized? Only through inverter or some power system it can be realized?
Only through inverter. If
Okay.
you make your
Yeah.
own power system after 6 phases, then you can locally feed your own machine. But otherwise,
Yeah.
we do not have 6 phase connection anywhere. Yeah, only through
Yeah.
inverter.
That's what. That's my question. Thanks.
Okay. So, is there any other question?
Sir,
Otherwise, we'll go forward.
yes, sir. Actually,
Yeah.
with respect to the previous question, sir, if
Yes.
same current is being pumped, it will not rotate, only pulsate, right, sir?
Yes.
Okay.
Okay.
And one more thing. Hello,
Yeah.
Bridget.
Yes. Yes.
Yeah.
Yes.
So actually, like earlier, one stationary field, one plot you have shown, right? Very beginning, one stationary plot. Now, whatever we were discussing is like we have a stator poles, and then with respect to that windings. Once I'll give the winding to the stator,
Yes.
then I'm trying to create the my field, because by injecting AC current to the particular my to the pole shoe, means like that windings. Okay, so
Mm-hmm.
I'll try to create my field. So
Yes.
this is a rotating field. And
Yes.
earlier, whichever you have discussed, that is a stationary field. That some
Yes.
trapezoid you have shown. With
Yes.
so like now, like all the discussion is related to the synchronous machine only, right? So now we have a two fields here. So like doubly
Nothing.
like we have to
It is.
exact.
It is not related to synchronous machine or any machine. We had our problem.
Okay,
We had our problem. Do not try to relate to what we will relate to that eventually. So as of now, just try
okay,
to go in flow. So for this case, we saw that we need to have two fields, and in order to have
okay,
continuous torque production, either we need to have the two fields stationary with respect to each other, or they must be rotating at the same speed. So for the
okay,
stator field alone, stator, because it's stationary, it's not rotating, right? So first we are looking,
okay,
stator is stationary. So can we have
okay.
stationary magnetic field, stationary stator magnetic field? We saw that yes, we can
So
have,
yes,
if
yes,
we excite it with
that
DC
one.
current, then we
Okay,
can have. Next, we are
okay,
trying to see, can we have rotating magnetic field by exciting some kind of current in stator windings, and the
okay.
answer is yes, we
Just a
can
minute.
have.
Just a minute.
Yeah.
So now, like one is stationary and one is rotary, correct?
Yes. Yes.
Rotational. So here, like first case, whatever you like evaluated is like by injecting DC current.
Yes.
Okay.
Yes, this is
So
the case.
whatever we
Yes.
have seen, this one is the DC current. So
Yes.
then again, the whatever the point with respect, again the same with respect the same, that is also same stator only. Now we were
Yes.
trying to inject with the AC, and then how
Yes.
magnetic field it is being created. Just we were seeing the scenarios, right?
Yes. Yes. So
So
just the
now
same thing,
again,
if we are injecting sinusoidal current, then we can see that the field axis does not change, but it pulsates, it reverses, it
yes,
flips. Yeah. Yeah, go ahead.
okay. Just a minute. Once again, you please repeat with the DC current that like just inject that. Try to inject the DC current so that how
Yes.
it that any animation is there for that.
Even if there is animation, it will not change, right?
Okay.
So it's the DC current, so with time it remains the same, it's the DC current.
Yes.
So current is like this, it's constant. So magnetic
Correct.
field is also like this, constant.
So whatever the plot we are seeing, this is with respect to DC current. It is same only. It will not change.
It
Like
will remain
the
same with time.
okay. And one more thing, like now, which book you are following to
No books.
this session? No, no.
No books.
Normally, any books if you
If
are suggesting, let me just refer it
uh,
so that it can be helpful.
so see, if these contents were there in some book, then I would not be teaching that, right? So yeah,
Correct, correct.
it's
But any book or any references, something if you are something, it will be helpful for us, like normally
I do
to
not
refer
know.
it.
I do not. I have gone through many books, but uh, I have not got it in any books like this. The
Okay.
way I'm discussing right now.
Yes, yes, yes. That's what. Like, just I wanted to know. It is like the sequence, how you, however you are following. That is very good. So somewhere in any book being it is mentioned or not, just I wanted to know actually.
Yeah, yeah, yeah. Okay. But yeah,
Okay.
unfortunately, it's not there.
Yeah. Okay. Fine. Fine. Okay. You continue. Yeah.
Yeah. Okay. Thank you.
Samrat,
Yes.
just a minute. I have one question here.
Yes.
Yeah, can you go to three-phase two-pole machine diagram which you have mentioned? Yeah, here.
This one.
So
Yes.
here we are spatially distributing the three phases. Okay, so the excitation of three phases, suppose it is um, like a zero sequence current. All phases are starting at the same point in time. Will it be a pulsating magnetic field or rotating with a higher
It will be a
magnitude?
pulsating magnetic field only, because if you have zero sequence, what do you mean by zero sequence? Zero sequence is constant DC, right, into all the phases.
Mm.
So if you have constant current, so if you have IA, IB, IC, or IR, IY, IB, whatever, if all the currents are constant, if everything is like this, then it will be south pole, north pole, south pole, north pole, like this, and you will have flux lines like this, right?
Okay.
It will have flux lines like this. This is the structure that you will have, right? It
Okay.
will be
Okay.
stationary, it will
Yeah.
not
Yeah.
rotate. It will be stationary, it
Okay.
will not rotate. But if you have, say, same current same current but sinusoidal through all the phases, then for some time it will be south, then it will become north. So for
Yeah.
it will
Yeah.
be similar to the case which I showed earlier, right? It is 0,
Yeah.
then
Yeah.
positive, then negative, then again falling to 0, then it will flip its sign, so it will become north pole, it will become south pole, like that.
Yeah. Yeah.
Yes, so we
Okay.
saw
Got it
that
now. Yeah.
only if we have uh, uh, three phase shifted axis, and if we inject with three phase sinusoidal currents, then only we can have rotating magnetic field. Actually,
Rotating.
this thing can be uh, seen also. Probably I'll discuss that right now rather than going to the next case. So
Yeah.
why does it actually rotate? So what we are doing actually, we are having so this is geometry, nothing else. So we have three axes. This is, say, one axis along the rear. So we are having this xy whatever, right? This is one axis. Then we have another axis that is uh, 120-degree shifted, right? This is another axis. So if the unit vector along the first axis, probably I will maintain color, that will be better. So this is first axis, this is second axis, and this is third axis, right? Now what is the unit vector along this axis? This is one angle 0 degree, this is one angle 120 degree, and this is one angle 240 degree, right? Now say we have some quantity which will plot along this axis. So the first quantity is, say, some x1 is equal to capital X sine omega t, let's say. So if I plot x1 along this red axis, whatever I have plotted, so at omega t equal to 0, x1 equal to 0, so we will have the tip of this thing, or the x1, if we plot it along this horizontal axis, then it will be here. Now as we go to omega t equal to 30 degree, then it will be x by 2, capital X by 2 here, right? Then if we go to omega t equal to 90 degree, it will become capital X, like this. Now as we go ahead in time, at omega t equal to 150 degree, it will again come to half of that. At omega t equal to 180 degree, it will come back to the origin. Then it will become negative, that is why that means that this tip will move in the opposite direction. It will go into negative peak, and again it will come back. So this is what we are plotting. Is it clear? So we have one axis at one angle 0, and we are plotting the quantity, this quantity at different time instance along this axis. If it is positive, we'll put the tip in the positive direction. If it is negative, then we'll put the tip in the negative direction, right? So if we have another quantity, say same magnitude, but same thing, basically say omega t equal to say as of now sin omega t, then same thing will appear. So omega t equal to 0, it will be here, then it will go like this, it will again reduce like this, it will come back to origin, it will flip, go to the opposite direction, and again come back. Similarly, if we have the three quantities, the third quantity, that is x3 equal to x omega t, then the same phenomenon will happen along the third axis. So we are
Yeah, it
putting
means
the
to say,
values of these three quantities along the along the corresponding axis. Yeah, go ahead.
yeah, you mean to say like it will be pulsating along their respective axis,
Yes,
magnetic axis.
yes,
Yeah, got it. Yeah,
that is what we are realizing here also, right? We are having three
yeah, yeah,
axes, and one the effect of one we have seen, it is pulsating, right? The same thing,
yeah.
we are just doing it mathematically or geometrically. Now if we have omega t equal to 180 minus 180 degree here, and here minus 240 degree here, now what will happen?
Now it will be rotating.
Now it will be rotating. If you just do
Yeah,
this math, you will find out that it will rotate. So for simplicity, for uh, convenience of everyone, let me just do it for omega t equal to 0 degree and omega t equal to 90 degree, let's say. So omega t equal to 0 degree, sine this one x1 is basically, yeah, at omega t equal to 0, r is 0. Omega t equal to 0, uh, YOLO, what is the YOLO value? Okay, okay, we'll just, yeah, okay, it is some negative value, right? It is some negative value, so it has to be here. Black only, it will be here, somewhere here. Then blue, if I go ahead, blue at omega t equal to 0 is the same positive value, root 3 by 2 positive value, so it is the same positive value. Now we have to see the net effect. Net effect, we can we have the first vector, that is here, we have the second vector, third vector is a null vector. So if we take the vector addition of these two, then our net vector is at at theta equal to 270 degree. Now if we do the same business for say omega t equal to 90 degree, you would say that x1 is maximum. So x1 is maximum, so it's here. Then other two are basically minus half, so uh, so it is half here, again minus half here. Now again if you take the net of all of them, you will find the net vector to be at horizontal, that is theta equal to 0. So as you have moved in time from omega t equal to 0, then it was at theta equal to 270 degree. Now as we move to omega t equal to 90 degree, the direction, the net vector has moved to 0 degree or 360 degree. So as we are moving, as we have moved ahead in time by 90 degree, the theta has also moved ahead by 90 degree in the anti-clockwise direction. So this is the mathematical basis for behind this rotating vector production, and you can see that we are doing the same thing. That is why I first discussed the pulsating field, which gave you this view that if we excite with sinusoidal currents along one axis, it is pulsating like that. It is the vector is basically pulsating, it's flipping after 180 degree. And same thing if we do 120 degree shifted in different axes, then same thing will happen, but the net effect will be that of a rotation, what we saw here. Yes, same phenomena is happening under each pole, but we are seeing the net effect, which is a revolving field. Yes, because it's already time, so shall we call it a day now?
Uh, Samrat,
Any question?
can
Yes.
you? I have one doubt.
Yes.
Can you go to slide number 11?
11. Yes.
Yes. Actually, I just want to know that when you are exciting with constant DC current,
Yes.
the stator, so this flux plot should be constant, like Tesla magnetic density should be constant, no, throughout the period. But
Yes.
you are trying to reverse the current, DC current, to plot this.
No, no, no. It's the same thing. It's along the angular position. So if it is positive under now north south pole, and it's negative under north pole. So where this is 270 degree theta,
Mhm.
270
Mhm.
degree theta means this position.
So just wanted to know, like, to plot this
Uh,
graph,
uh,
you have to like change the rotor position, or you have to
no, no, no,
change
no,
the
no,
current direction.
no, 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 nothing. I am injecting the same current. Here it is having dot current, here it is having
Mm.
cross current. Here it is having dot current, here it is having cross current. Now what I am
Okay.
doing is I am looking at the flux density on each point on this circle, red circle.
Ah, okay, okay, okay. Thanks, thanks.
That is what I am plotting here.
Okay, okay,
Now
thanks, thanks.
because it is under now south pole, flux lines are going upward, that I am taking
Mm-hmm.
as positive, and if flux lines are going in the radially outward, then I am taking it as positive. If it is radially inward, then I am taking
Okay.
it as negative. Is it
So
clear?
the corresponding magnitude of magnetic field density is like approximated value from your end. That's all. Or
Yeah, not
okay.
approximated. This is a simulation that I have done, and on
Um,
this circle I have seen what is the flux density at each point, and I am
okay.
plotting
So that
that
means
with data.
a rotor is like you are trying to rotate the rotor in
No,
this
no, 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 no,
simulation.
no, no. It's
No.
it's station. It's stationary. Nothing is rotating.
So,
But
like today, whatever we have discussed is with respect to the stator only. One case was with the DC supply, and one case is with the AC supply, right?
That's correct. Yes. The
but
rotor
And
does not.
one
this
more thing.
Yeah.
Yeah, yeah. Please
Go ahead.
continue. Something you asked.
Oh,
uh,
I was telling that
actually
even rotor does not have anything. Rotor is simply I have just put a cylindrical shell like this. It does not have any conductor, nothing.
Mhm. So,
Right?
my confusion
So
was like it is like B has positive values and
yeah,
negative
yeah, yeah.
values. So
Now you have got
when
it
you
right.
are plotting it, so I was thinking that okay, maybe you are reversing the current direction just because rotor is stationary. So
Yes.
that's why it got confused. Okay.
Rotor is stationary, and I am plotting the B values on the circle. On the circle, whatever is the
Okay,
B
okay, okay,
value, that I am plotting.
okay,
And if
okay,
B
okay.
is radially outward, I am assigning positive value to it. And if B
Okay,
is radially inward, I am assigning negative value to it.
okay, okay, okay. Thanks.
Yeah. And one small request, Samarji, like at the end of this particular all the magnetic field sessions, like
Yes.
just differentiate with respect to the DC motor and synchronous
Yeah,
motor
yeah, yeah.
and induction motor,
Yes, yes.
so that the differentiation will be more helpful. Like that will be the
We'll
conclusion
discuss.
for the session. So I feel
We
it.
will.
So
We'll
yeah,
have.
there all the confusions will avoid. Like everyone will have a one clear cut understanding.
Yes, yes. That is there in
Yeah.
the next in the upcoming slides. As you go, you will see.
Yes. Yes.
So first,
Yes. Yes.
first we are looking at this realization of stator magnetic field. Only two cases:
Yes.
stationary, rotating. So stationary, if you see, if I try to summarize quickly, the stationary magnetic field is there in DC machine.
Correct.
Produced by the stator magnetic field. Basically, the stationary stator magnetic field is there in DC machine. Now, rotating stator magnetic field is there in induction machine as well as synchronous machine. Right? Now, the differentiation
Yes,
you will
correct.
see will be in terms of how we realize the rotor magnetic field. That will be there. That will be upcoming.
Yeah. So that's what, like, after completion of this, one small tabulation, like from the like one conclusion points will make it. So it will be easy to refer it, and also it will, all the confusions will avoid. Like it will eliminate.
Yeah, sure.
Yeah.
Sure.
I have two doubts.
Okay.
One is you please discuss about two-phase machine. So you have discussed only from three-phase only. Discuss about two-phase only. Second thing is discuss about some symmetrical machines. What is symmetrical machine? In some textbook they will use this is symmetrical induction machine, symmetrical synchronous machine.
Symmetrical induction machine is nothing but the three-phase machine that we that we refer to things widely. So symmetrical machine, symmetrical induction machine, symmetrical synchronous machine is nothing but the uh, regular three-phase induction machine or synchronous machine.
You know that the book Alexander book, some like that. Those book will refer as a symmetrical machine.
Yeah.
That is why I'm asking. There are two tours, and also I will give one suggestion. Please, you make a Q&A session at the end of the session. Otherwise, you cannot complete the class because there are variety of people here. During the class session, some doubt will clear automatically. After the class, you keep the Q&A session because variety of people here. Some people are working, some people are students, some people are new. So it will unnecessarily take some time. So
Okay,
keep
surely.
the
So
Q&A
from
section in the last of because you have something to say. No, if you go through these kind of questions, you will forget what to say. So
yeah,
please, I'm just suggesting. Okay, keep it
yeah,
in
sure.
the end of the
Yeah,
session.
it would be a good. It is a good suggestion. So
Okay.
probably
Yes.
I'll discuss for 50 minutes and the last 10
Okay.
minutes and the last
Yeah. Yeah.
I would stop for the Q&A.
Yes, because
That
you
is a
have
good
a
suggestion. Yeah,
55
you can
slides,
have.
but only uh, 20 slides only it will covered. Okay.
Yeah,
Okay, sir. Yeah, discuss about three-phase induction machine.
yes. No, no, I am not discussing three-phase induction machine. I am discussing how to produce rotating magnetic field by exciting something in stator. As
Okay,
of
but the
now,
two-phase
up to this.
two-phase induction machine, you cannot say that you divide 360 divided by 2, and also two-phase means angle between the two currents are 180 degree. That is why I'm asking.
Okay, so two-phase machine is simple. So whatever I have discussed with respect to three axis, I'm just indicating that because uh, uh, that will clear this thing up, and that will not come in the upcoming things. So for three phase, we are having three axis like this, 120 degree phase shifted. For two phase, we will have 90-degree phase shifted, right? And if you do the same thing whatever I have done earlier, that is putting some value and pulsations along that and taking the net value, the same thing if you put some current. So suppose you have the a phase or x phase axis along horizontal and y phase axis along the vertical direction, and if you inject some current ix im sine omega t and iy current at I sine omega t minus 90 degree, you do the math, you will find that the same rotating magnetic field you can realize. So yeah, two phase machine is also possible if you have two phases, and if you put your two phases vertical to with respect to each other, and if you excite them with 90-degree phase shifted currents, you can see I can just indicate for say 0 degree. For 0 degree, what is that? I equal to capital I equal to 0, and this is minus, right, omega t equal to 0, that means sine of minus 90, so minus I, so it is here. Now if you go to omega t equal to 90 degree, then this will become I and this will become 0, so my vector is here. Now if you go further, or at omega t equal to 180 degree, you will find your vector to be here. And similarly you will find that whatever thing was happening for 3 phase excitation, or in general for m phase excitation, you can have the same thing for 2 phase machine also. If you have your 2 phase axis phase shifted by 90 degree, and if you inject 90 degree shifted currents, you can find that you have the same thing. So that is about 2 phase machine.
So that the 360 divided by n formula will not valid for
Will
two
not
phase machine.
yeah, for 2 phase machine it will not hold.
And one more question. For the simulations, which software you are using?
So initial part I was doing in FEMM. Now whatever animation type of thing I will be showing, and I have shown, those I have used in ANSYS.
Okay, ANSYS Maxwell.
Yes.
Okay.
Sir, is there any significance of this traveling wave?
We want the magnetic field to rotate, right? That is what we see here in in our basic need of to have continuous torque production. We need our stator fields to be either stationary or rotating. So yeah, it is significant. It is significant for our motor to rotate, and we'll see how when we go to the rotor magnetic fields. Okay, is there any other question? Otherwise we'll close for today and we'll continue on the next day. Yeah, no more question, then we'll close. Stop recording.